Okay, so hello everyone. Welcome to our this week Rogers in Efficient AI seminar. And today we're very glad to have the Professor Zhuo Feng from the Stevens Institute of Technology to give us this talk. And Professor Feng received a bachelor degree from the Shenzhen University and a master degree from the National University of Singapore and a PhD degree from the Texas A&M. And he's currently associate professor in the Department for Electrical and Computer Engineering at Stevens. His current research interests include high-performance spectral methods for machine learning and the scientific computations, VSI design and computer-aided design, and also heterogeneous parallel computing. And he received the NSF Career Award and also the Best Paper Award from the ACM Design Automation Conference. That is the best conference in the EDA field. So very prestigious award. So now let's welcome Professor Feng to give us this talk.
Yes, thank you, Paul, for the very kind introduction. So today the title of my talk is High Performance Spectral Methods for Scalable Graph Learning, Adversarial Robustness Evaluation, and Electronic Design Automation. So I would like to thank my students as well as our sponsors for the related work. Okay, so today I think we are observing increasing complexities in large networks as well as graphs. Although these graphs may represent different things, right? For example, you have transportation networks, social networks, and circuit networks, where all the nodes and edges are representing different things. We do observe the same trend. Basically, these graphs are only getting bigger and bigger, right? For example, data and social networks are evolving every second, and the circuit networks are doubling in size every other year. Okay, for our ECE students, right, we are more interested in hardware development. Right? As you can see, nowadays, chip designs are observing increasing complexities, right, from the device level to the system level. Right, then the question is, how can we cope with the faster growing complexities in chip designs? Okay, so here is the outline of my today's talk. I will introduce a very interesting and efficient method for handling those large networks. And then I will show its applications to graph learning, machine learning, as well as EDA problems. Okay, so don't hesitate to interrupt me if you have any questions. I believe some topics may be still new to most of us, right? Okay, so here is the idea of graph specification. Okay, so graph specification tries to find a simpler graph which can well mimic the original graph with much smaller number of edges. This reduced graph size will allow us to design very fast numerical graph algorithms. For example, we can use this simplified graph to solve partial differential equations or sparse matrices much faster. And also we can develop more efficient graph learning algorithms. Potentially, it will also allow us to handle very big data sets on very small devices. For example, we can probably do PageRank computations on our mobile devices locally. Okay, so here is a background introduction to existing method for graph specification, right? Decades ago, researchers introduced a cut specification concept, which tried to simplify the graph that preserve the cuts between nodes. So basically, the idea is that we will sample each edge with a given probability. If the edge has been chosen, then we will adjust the weight so that the cut of the original graph can be preserved in the specified graph. About a decade ago, Spearman and Tan introduced the concept of spectral specification, which is actually a stronger notion because it can not only preserve cuts, but also eigenvalues and eigenvectors of the Laplacian matrices. If you look at the graph-based properties, it also preserves the pairwise distance resistance distance on the graph, the cuts, low dimensional graph embeddings, stationary distribution of Markov chains. So in this talk, I will focus on spectral specification, which also reflects our recent efforts. Okay, in order to understand spectral specification concept, the first thing I need to explain is called graph Laplacian. I think for E students, right, it's nothing new, right? But just admittance matrix in our resistor network. I believe most of the students have taken courses related to circuit analysis. So if you look at the graph Laplacian matrix, exactly the admittance matrix we use for circuit analysis, it has some nice properties. For example, this matrix is a symmetric diagonally dominant matrix with non-zero, with non-negative eigenvalues. Researchers show that these eigenvalues and eigenvectors are related to some important graph structure properties, which therefore deserve deeper understanding. So that actually motivates people to consider studying graph properties using its Laplacian matrix. To this end, this Laplacian quadratic form needs to be explained first. Okay, so here is a definition of quadratic form related to Laplacian matrix. Okay, let's look at this Laplacian in an easier way. So we will consider the x vector as a voltage vector assigned to all the nodes in the resistor network. We also consider the edge weight as wire conductance, which connect those nodes. Then the quadratic form is simply the Joule heat produced by this resistor network, given that voltage vector. For example, right, if we know the node voltages across the network and edge conductance, we can simply compute the Joule heat dissipation, which is exactly the Laplacian quadratic form. So next, I will show how to identify two similar graphs using these quadratic forms. We say two graphs are sigma spatially similar if for all real vectors x, their quadratic forms are very similar. So equivalently, right, if two circuit networks are similar, they must dissipate the same amount of energy under the same voltage distributions. So we will use this to quantify the similarity of two graphs in the future. We can show that two spatially similar graphs will have very similar eigenvalues and eigenvectors of the Laplacian matrix. Also, they have similar effect resistance distance on the graphs, cuts, embeddings, or stationary distribution of Markov chains. Because this spatially similar graph will preserve a lot of important properties of the original graph. So our hope is that we can always extract useful information using the simplified graph instead of the original one to speed up our program or application. Then how can we compute spatially similar graphs with much smaller number of edges? There is some existing work proposed by Spearman about a decade ago based on the near linear time algorithm. So this algorithm is actually very simple. So the idea is that we will sample each edge with a probability which is proportional to the edge's effect resistance. Okay, so for each edge resistance, we can actually compute it using this formulation, where this LG pseudo-inverse of the Laplacian matrix is also considered the inverse matrix, right, of the original Laplacian. Once we get this effect resistance of each edge, we can sample the edge according to this probability defined here. As you can see, the probability will be proportional to the ratio of the effect resistance of the edge and the edge resistance. So this actually makes sense. Suppose we have two communities connected by a single edge. Then the effect resistance of this edge will be equal to the resistance of itself. Then we have to sample the edge with 100% probability because it's so important for connecting two communities. However, if we have some parallel bridges connecting to the two communities, which means there are multiple passes connecting them, then the effect resistance will be much, much lower between the two nodes. Therefore, we can sample each edge with a much lower probability. Then we can sample the graph edges according to this probability to obtain the specified graph, which also preserve the most important spectral properties. However, the challenge is that it needs to solve this Laplacian matrix multiple times in order to get the effect resistance for every edge, which can still be computationally expensive for large graphs. So in today's work, we are going to introduce some alternative ways for solving the problem. So to start with our method, we have to introduce the concept of spectral graph partitioning. So here I'm illustrating a very simple graph with 5 nodes. We also define a node set S to include 2 nodes. Then if we assign value 1 to the 2 nodes inside the set S, as well as 0 to the node set outside S, then we can easily show that the quadratic form will be equal to the number of edges connecting the 2 clusters, which is defined as a cut in the graph. So this actually indicates the connection between the quadratic form and the cut in the graph. Instead of restricting the node values to hold only values 1 and 0, we will do some relaxations, allowing those node values to be continuous. In this case, we are able to find the maximum cut in the graph by solving a maximum eigenvalue problem associated with this quadratic form, as well as finding the minimum cut in the graph by solving a minimum eigenvalue problem associated with the Laplacian matrix. So for the later one, it's actually more meaningful because it's usually required for graph partitioning task. For example, we can always compute the eigenvalue and the eigenvector corresponding to this optimization problem, and then use the eigenvector to cut the graph so that we will have a very distant solution. So this has been already used in many applications for graph clusterings or dataset partitioning task. So next, I'm going to introduce our idea for finding a spatially similar sparse graph based on the previous concept. So here I'm illustrating 2 graphs. Graph G represents the original graph, and graph P represents some initial subgraph, which contains edges of the original graph. Okay, so based on the eigenvalue and the eigenvector information, we can now understand that by solving this generalized eigenvalue problem, we will have to find a cut that is maximum in the original graph and minimum in the subgraph. Then the corresponding ratio will be bounded by the largest eigenvalue of this generalized eigenvalue problem. So to show a simple example, in this case, we find this cut to have a largest mismatch when compared with the subgraph P. We find 6 cuts in the original graph and only 1 in the subgraph. Therefore, we can show that lambda max of this generalized eigenvalue problem will be no smaller than 6. Our research proposed some method which try to find new edges to be included into the subgraph P so that we can minimize the largest eigenvalue, lambda max, which definitely will minimize the mismatch between the 2 graphs considering the cut ratios. For example, we introduce another new edge to this subgraph so that the cut mismatch now becomes smaller. This can be achieved by minimizing the largest eigenvalue. So this idea is conceptually simple. Then how can we implement this in an efficient way? So we will start with some very good spanning tree subgraph as the initial subgraph construction phase. In this tree approximation, we can always define the distortion due to the tree approximation. For example, in the original graph, node P and Q have a distance 1, but in the spanning tree graph, it has a distance of 7. Therefore, the distortion brought by this PQ edge will be 7. To measure the total distortion due to this tree approximation, we can simply sum up all the stretches of the edges in the original graph. Theoretical work already showed that the total distortion will be bounded by this m log n log n, where m corresponds to the number of edges in the graph G, and n represents the total number of nodes. This is a very important kind of spanning tree, which can be used for constructing the initial subgraph P we introduced before. By doing some further derivations, we can show that this total stretch is actually equal to the trace of the LP pseudo-inverse LG, where LP represents the pseudo-inverse of the specified graph or the subgraph, and LG represents original Laplacian matrix. This also means the spectral similarity will be bounded by the largest generalized eigenvalue lambda max we introduced in the previous slide.
为啥不能说中文呢？明明是中国人，真是。
Hello?
Yeah, you can continue, yeah.
Okay, so yeah, as you can see, now the spectral similarity will be bounded by this largest generalized eigenvalue. Therefore, if we can reduce this lambda max by adding new edges, we can immediately improve the spectral similarity between two graphs. Okay, so here is the idea we introduced in our recent work, which try to find important edges to be included into the initial specific graph P. For example, we can find one important edge so that the largest eigenvalue will be immediately mitigated. And then we can find the second and the third so that the total mismatch between the two graphs can be immediately improved. This is actually backed by some recent research study, which show that there will be not many large eigenvalues associated with this tree-structured sparse graph, right? Basically, the number of eigenvalues greater than stretch over k, right, will be smaller than k. So that means the largest generalized eigenvalue distribution will be very sparse and only require a small number of additional edges to be added in order to reduce those eigenvalues. Okay, so next I'm going to show some results based on this concept. To illustrate results in a better way, we will show the concept of spectral graph embedding. So the spectral graph embedding aims to visualize a graph in the lower dimensional space based on the first few eigenvectors. The reason we want to use eigenvectors for graph embedding is because we can show that if the eigenvalue is very small, then the node values across the neighborhood will be very similar. So that actually means there will be a very smooth transition across the eigenvalues across the neighborhood node. Therefore, we can compute a few eigenvectors associated with the Laplacian matrix and then use those eigenvectors as the node coordinates, right? For example, we will use the first 3 eigenvectors for setting up the coordinates x, y, z for plotting the graph in 3-dimensional space. Then you will get a very smooth illustration of the graph structure. So using our proposed method for specification, we can show that given the original graph, which is pretty dense, where the edge to node ratio is 2.9, we can approximate the graph structure with much fewer edges. For example, here in this graph, we use a much sparser one to achieve the largest eigenvalue of 10. That means the biggest mismatch between the two graphs will be no greater than 10 cuts. If we further reduce the number of edges, we can find some lambda max equal to 40, 90, 160, and 500. As you can observe, the embedding structure will be slightly changed, but it still preserves the original structure well, even with a tree-like structure. As you can see, right, in this last graph, the edge to node ratio is 1.02. So it's really tree-like structure. If you are interested, you can also use our graph software for plotting some graph structures. We also introduced some optimization frameworks to further size the edge weight in the subgraph. Since we have removed a lot of edges, we want to make the remaining edges much stronger. This can be actually done by using a gradient descent optimization framework that has been proposed a few years ago. As you can see, when we only introduce a small number of edges in the subgraph, the original embedding may be pretty bad, but after the scaling of the edge weights, we will get a much better embedding. Okay, so next I'm going to show the potential extension of the spectral algorithm for graph compression and machine learning applications. So in spectral graph compression task, we not only want to reduce the number of edges, but also the number of nodes. This can be done by finding a nice embedding in the low-dimensional space, and then do the clustering in the embedding space. By merging the node in the neighborhood, we can form some supernode, which will represent a group of nodes that are strongly coupled. In this way, we are able to reduce the size of the graph without perturbing the structures of the original graph. Because most machine learning tasks are extracting the features of the graph structure, which therefore will not be impacted by this compression process. So we can also understand this graph compression procedure as a filter on the graph, right? If we treat the low frequency eigenvectors as some low frequency signal components in time domain, then this low frequency component will encode the graph structure properties. Spectral compression will be able to preserve the original low frequency eigenvectors with a minimum number of edges and nodes, which therefore can be considered as a low pass graph filter. As you can see, after removing some of the nodes or coarsening some of them, the eigenvectors of the fundamental modes will still be preserved in the eigenspace. So this is some algorithm we introduced in recent years for spectral graph compression. I'm not going through the detail. Instead, I'm going to show some interesting results. Through spectral compression, the benefit is that we only introduce local errors, which can be easily removed by applying smoothing operators on the graph solution. For example, after we coarsen the graph aggressively, the embedding will become quite disturbed for a 2D mesh. As you can see, there is a very big hole here due to the missing edges or nodes. Fortunately, those embedding solution errors are only local. We can immediately improve the embedding by applying some smoothing operators. After applying one step Gauss-Jacobi relaxation to the solution, as you can see, the node embeddings will be moving towards the correct locations quickly. if we do 10 steps smoothing, we can almost recover the mesh structure. After 50 steps embedding, we can almost completely recover the 2D embedding of the original 2D mesh. So this is a very important feature we can leverage for many machine learning tasks. So in 2020, we introduced the graph zoom in collaboration with researchers at Cornell University. This method is based on the graph compression, right? Especially, we will, particularly, we will do spatial specification and coarsening to the original graph so that we can apply the graph embedding algorithms on the reduced graph. Because this reduced graph only introduces local errors in the embedding result, then we can use some local refinement procedure to fully recover very accurate embedding solutions. So we achieved significant speed up and even accuracy improvements on public domain data sets. For example, for large graphs, we achieved over 300 times speed up, right? Also, we can improve the macro F1 score for the Friendster data set with 8 million nodes and 400 million edges. Okay, any questions so far? Okay, if no questions.
By the way, I noticed that the examples that you give appear to have this mesh structure. And I was wondering how much of this depends on the planarity of the graph.
Okay, so this is a very good question. So as you can see, right, in the typical physical domain meshes, right, we usually have a very nice structure which can be visualized in low-dimensional space. So that actually implies the graph structure is dominated by a few smallest eigenvalues and eigenvectors. Okay, however, if the graph is non-planary, for example, it's a social network graph, or some more complicated graph which doesn't have any structures, then we will need many more eigenvalues and eigenvectors to preserve the structure. So you can always increase the number of eigenvalues and eigenvectors in the preservation phase to kind of more non-planary, right, graphs. Does this answer your question?
Well, partially, because for very large graphs, computing the spectra is not necessarily simple.
Yes. So instead of computing those eigenvalues directly, we will use the coarsening method and smoothing factors to approximate those eigenvectors, right? This has been introduced in our recent work published in 2021 WSDM conference. So in this work, we introduced a multi-level framework, which is similar to multi-grid, which allow us to compute many important eigenvectors in an approximate way, leveraging the graph coarsening kernel.
Fantastic, fantastic. Thank you.
Okay, thank you for that question.
Sure.
Okay, so here I use mesh because it's kind of easy to visualize, but definitely there are some graphs which are not suitable for this two-dimensional visualization at all. So that's why in graph embedding tasks, right, we typically have the vector dimension of over 100, which will be sufficient for representing the structure of typical graphs we have seen in social networks or in other data networks. Okay, so the next task is just opposite to the previous graph embedding task. In graph embedding task, we are given the graph structure and we try to find the vector representation of each node. But here, for this research topic, right, we are given a lot of vectors and we try to construct a graph from those data vectors. So that's why we call it graph topology learning from data samples. So to achieve this goal, we are looking at a graphic model approach. Okay, so to start with this topic, I will first try to introduce this multivariate Gaussian distribution with this probability density function shown here. So here I also visualize a two-dimensional case. Okay, so in order to learn a graph from data sets, which can be high dimensional, right? We will try to formulate the problem as a Gaussian Markov random field estimation problem. The goal is to maximize this probability density function by optimizing this precision matrix, which also should be sparse. As you can see, here we have 8 vectors, which we try to connect through the graph structure. In order to determine the connections, we will use this maximum likelihood estimation method to make sure each edge will only connect two variables that are conditionally dependent. So if x1 and x2 has no conditional determinacy, then there will be no edge connection. So in this case, each edge will correspond to the conditional dependence, and each node corresponds to each vector or each variable. However, the challenge is that traditional method based on convex solver will not scale to large data sets. How can we find this precision matrix in a more efficient way? So here is the approach we proposed in recent work, which is called graph-per algorithm. So instead of solving some original precision matrix with no constraints, here we will set up additional constraints, which restrict this precision matrix to be a Laplacian matrix of a graph plus some delta term. So by implying this additional constraint, we can prove the obtained precision matrix will correspond to some attractive Gaussian Markov random field. So by imposing this constraint, we are able to develop a very efficient spectral method for GMRF estimation. So if we take partial derivative to this formulation with respect to each graph edge weight, then we can show that it's equal to the graph spectral embedding distance between the two nodes minus the Euclidean distance between the two vectors. So this actually implies that if two nodes or data samples are far away on the graph, but are very close in the Euclidean space, then we should use an edge to connect them, because this edge will significantly improve our optimization solution, right? Because if the gap between the embedding distance and the data distance is large, the gradient will be large. Using gradient-based method to solve this convex problem, in that way, will be much faster. So I'm not going to cover more details of this. Instead, I'm going to use some simple algorithm flow to illustrate the concept. So here, suppose we are given a large number of high-dimensional data samples. Then we will construct some initial graph using some naive approaches, which may not be good enough at all. Next, I'm going to find the spectral graph embedding distance between every node by performing a graph embedding procedure. So as you can see, we will compute eigenvectors of this existing graph and assign low-dimensional vector to every data sample. By checking the distortion in the embedding space as well as in the Euclidean space, we can quickly tell if this data sample pair need an edge to connect them. If the distortion is large, then we will introduce a new edge to connect them, right? Because the graph distance is much higher than the Euclidean distance between the vector space. By iteratively doing so, we are able to dramatically improve the estimation. After we can no longer find any new edges that has large distortions, then the iterations will converge, which actually corresponding to the case where the gradient equal to 0, Therefore, the convex normalization problem converge. So in this paper, for the first time, we show the connection between spectral graph theory to the existing graphic model estimation problem. So we apply this new method to many applications, such as spectral data clustering, where we try to identify the edges to be included to some existing two nearest neighbor graph at the beginning. As you can see, by adding a small number of new edges, we can drastically improve the eigenvalues of the Laplacian, therefore the distortion of the samples in embedding space. The spectral embedding also allows us to find the clustering of the data sets, right? Without using additional edges, we only get accuracy below 20%, but adding 10 edges, we already achieve 91% accuracy for classifying this MNIST data set. We can also apply this graph topology learning method for multi-level data visualization. We can build multi-level graph structures corresponding to high-dimensional data samples, and then by performing t-SNE algorithms on the coarsened graphs, we are able to speed up the t-SNE algorithm drastically. For example, after reducing the graph by 20 times, we can achieve over 60 times speed up for t-SNE visualization, which doesn't give us any degraded result. In the recent collaborative work with Cornell researchers, we proposed graph topology learning for robust graph neural networks. As we know, by introducing small perturbations to some graph structures at input, we can drastically decrease the precision of the classifier in graph neural networks. In this example, as you can see, by introducing some attacks, the accuracy will drop drastically. Then how can we make sure this will never happen to our data set? In the Scarlet framework, we introduced a graph purification procedure, which tried to reconstruct a new graph using the first few eigenvectors of the original graph, which can be already polluted. After learning this new graph structure, we are able to train a very robust model, which will not be sensitive to any attacks. We can show that this new graph structure will preserve the low rank properties of the original graph and remove the high rank attack introduced during the perturbations. We actually achieved over 10% accuracy improvement, as well as 50 times runtime speed up. In the same time, we studied spectral method for quantifying the robustness level of any machine learning models. So in the past, researchers showed that by adding a small perturbation to the input data samples, we can mislead the model. Traditional ways to quantify the robustness of these models are based on white box method, which require the knowledge of underlying model parameters. For example, we need to understand the neural network structure as well as their parameters in order to calculate the Lipschitz constant. If the model have a very large Lipschitz constant, it implies potential risk due to this adversarial attacks. In our recent work, we propose some black box method, which doesn't require any knowledge of the underlying machine learning model. Our method is based on the mappings between the manifolds for the input data and output data. So as shown here, suppose we can construct some manifold for the input data space, as well as a manifold for the output data space. The output data samples are obtained by passing those input samples through some machine learning model, such as a deep neural network. Our goal is to quantify the largest possible distortion on the distance. For example, if we can find a data sample pair, PQ, that is very close to each other on the input manifold, but very far away from each other on the output manifold, we believe this model will be not stable and can be easily attacked. We can also theoretically prove that the largest distortion of the node pair distance will be the upper bound of the Lipschitz constant of the given machine learning model. So to characterize this Lipschitz constant using this approach, we propose to construct graph-based manifold for both the input and output data samples. And we use resistance distance for quantifying the distance between two nodes on the input and output graph. Because effect resistance distance are closely related to the Markov chains, right? Mixing time of random walks, right? Also, it's related to many important features of diffusion models. We show that the largest eigenvalue of this Ly pseudo-inverse Lx will be the upper bound of the largest distortion for distance distortion calculation. Also, in our experiment, we observe this is a tight estimation. Okay, if there is any question on this, please let me know, right? Here, I just stress that in this approach, we don't require any model parameters to be given. Instead, we only need to have the input data samples as well as output data samples, which are going to be used for setting up the graph-based manifold. Then we can compute this eigenvalue using those two Laplacian matrices to quickly characterize the upper bound of the model Lipschitz constant. This work has been published in 2021's SAML conference. So a higher space score means a higher Lipschitz constant, which also means a lower adversarial robustness level. We can further extend the global Lipschitz constant to local Lipschitz constant, which is related to each single data sample. So here, as you can see, we have a graph manifold constructed for input space and another graph constructed for the output space. If two data samples are very close to each other on input, but far away from output, using this special embedding method, we can quickly identify these non-robust samples. Then, if you apply a test to these non-robust samples, we can easily mislead the model prediction. So, as an example shown for the MNIST data set, where we are embedding the input data set as well as the output from the neural network. As you can see, our model identifies that the most non-robust samples are related to digital image 9 and 4, because these two digits are very close to each other at input space, but they have been mapped to distant locations on output manifold. So this kind of large distortion means these two kinds of data samples may be quite non-robust and can be easily attacked. We also observe the next non-robust data digits are 7 and 1, right? Which are very close to each other on input, but far away from each other at output. So we propose SPADE based on the previous ideas, right? Which try to construct input and output graph-based manifolds and quickly compute the highest distortion by solving the Laplacian matrix eigenvalue problem. Then we can always identify the top non-robust data samples, and then we are going to adopt much stronger defenses to these non-robust samples during the training phase, so that the final model will be robust to adversarial attacks. Okay, our results show that the space score can truthfully reveal the model Lipschitz constant. So in this case, increasing epsilon corresponds to increasing robustness of a machine learning model trained through adversarial training algorithms. As you can see, the original model without any adversarial training has a spade score of 42. But if you train the model using epsilon equal to 0.3, which is a pretty strong defense, the Lipschitz constant decreased to 33. For the ResNet structure, we observe the same structure, same result, right? Because ResNet had more layers. Therefore, the Lipschitz constant is significantly higher. But after the adversarial training, the Lipschitz constant evaluated using our method has been decreased from 400 to 80. We also adopt these space scores of each data sample for robust training by applying stronger defenses to the non-robust samples. Then we get some promising results. Okay, in the last, I will quickly go through some related work in EDA field, which may not be closely related to any machine learning tasks, but it's actually important for many hardware designs. So in order to design any chips, we have to first simulate the circuit. However, nowadays circuit designs are so large, we can no longer afford the high runtime. While traditional fast spice tools may not be accurate enough, we propose some new method which will allow very scalable yet very accurate simulation of large circuit designs. Okay, so I don't want to go through many details of the math, but I will just show the basic challenge, right? In order to solve a circuit simulation problem, the key challenge is to solve this nonlinear optimization problem, right? Which can be done by iteratively solving this Newton-Raphson problem, right? We are going to solve very large Jacobian matrices from a given circuit structure. This will be the main bottleneck. So there are some iterative methods for solving sparse matrices proposed in the past. Basic idea is that given some matrix AX equal to B problem, right? We can show that the solver will need this many iterations to converge to a desired accuracy level epsilon. However, this iteration number is controlled by the condition number of the matrix. If the matrix condition number is large, it may need many iterations to converge to a correct solution point. That's why people introduce some preconditional solvers, which will try to find some approximate matrix B, which is very similar to A, so that we can solve this B inverse A instead of the original matrix A directly. The hope is that the condition number of this B inverse A is very small. Then we can solve the problem in just a few iterations. So here the challenge is that how can we find the matrix B that almost has the same set of eigenvalues of matrix A? This is exactly corresponding to the non-preconditional case. So in the following research, I'm going to show you how to use spectral graph specification to find very similar circuit structures that can be easily solved using some iterative solver. Therefore, we can accelerate the circuit simulations in a very effective way. Okay, so we apply this method to some nonlinear RF circuit simulation tasks, which actually require to solve a nonlinear differential equations in the frequency domain. So the concept is pretty simple, right? Given some nonlinear circuits, we will convert all the waveforms like voltages and currents into frequency domain. Then we will set up nodal equations in the frequency domain to make sure they satisfy the Kirchhoff current law. Traditional shooting method may not be able to handle distributed devices, while spice simulations may take many iterations to converge. So our recent work tried to solve this problem based on much faster Jacobian matrix solver. Okay, so in this frequency domain circuit problem, right, you can show that Jacobian matrix will demonstrate some block diagonal forms, right? Essentially, we are going to perform FFT to convert time domain signals into F domain components in the C and the G matrices. Then we are going to solve the system matrices in frequency domain and then convert those results back to time domain through the inverse FFT operations. Basically, the time domain sample need to be collected according to the Nyquist theorem to preserve the useful frequency components. I think this is kind of problem more circuit related stuff. I will quickly go through them, but the basic concept is pretty straightforward, right? We sample the circuits, nonlinear RF circuit in time domain, and then we try to find some representative matrix patterns, and then we apply spectral specification to these matrices so that we can construct the frequency domain matrix preconditioners for solving that harmonic balance problem. As a result, we are able to significantly reduce the number of fill-ins in the block matrices for harmonic balance analysis, right? We show that 60% edge reduction in time domain circuit analysis will result in 50 times matrix factorization speed up for harmonic balance simulation. We do observe very good speed ups on parallel CPUs as well as GPU implementations of the algorithm. This again shows a potential benefit of spectral graph specification in many circuit simulation tasks. I think one important benefit of our method is that for each circulated matrix block, we are able to preserve all the frequency domain interactions. Therefore, this kind of approximation will allow us to faithfully capture the strong nonlinearities in the typical RF circuits, while traditional method that try to use a block preconditioner for approximating this matrix may fail for a strongly nonlinear case. So as a result, you can see that in our method, if we increase the nonlinearity of the RF circuits, our method runtime doesn't increase, while the traditional preconditioning method will increase very quickly. Okay, so that's the last page. Thank you for the invitation. And if you have any questions, please let me know.
Thank you, Zhuo. Thank you very much for a great talk. Questions from the audience? I think there are some questions in the chat box.
Oh yeah, I see that. Okay. I'm quite okay. Coursening, do you have a result reporting work log? Okay, I think the runtime has been reported in our paper. I would say the coarsening phase only requires some sparse matrix operations, which can be very efficient on many core processors, right? These days, we are trying to accelerate those things on GPUs. But even for CPU implementations, right, using Julia, we already obtained some interesting, very, very good speed up. Do you have any thought on the trainable loss measuring difference between two graphs? Thought on the trainable loss. I know graph matching is needed to address invariance perturbation. Okay, so I think, yeah, you're proposing some very interesting problem, right? So this is related to the measuring, how to measure the distance between two graphs, right? Which may not have the same number of nodes. I would say there are many different ways. In our work, we started to look into the issue, but there is a paper published by MIT researchers in recent years. They try to use tree movers distance to measure the distance between two graphs of different nodes. If they have different edges, right? They have different number of edges, but the same number of nodes. You can always use generalized eigenvalues to check the distance between the two, because it's an upper bound of the maximum mismatch between the cuts of the two graphs. I'm not sure if this actually answers your question. So you mentioned some trainable loss. I'm not quite clear about this definition. What is so-called trainable loss?
Hi, Dr. Hi, Dr. Kirker. I mean, I want to design a differentiable way to minimize the because I want to predict a graph with its nodes and the edges simultaneously. So I'm thinking if there is any way to design a decent loss that we can minimize the loss via gradient descent. So
Okay,
yeah.
I see. So James, you are trying to first find the mapping between the nodes, right? So basically you want to identify the node pair mapping of different graphs, and then you try to measure the distance between the two graphs, right? Is that true? Or
Yes, but the key challenge is that so because the predicted graph and the ground truth graph, in my case, might have different number of nodes. So I'm thinking how to address this problem.
yeah, I think you can always use a concept related to graph isomorphism algorithm, right? Basically, MIT researcher proposed some graph isomorphism network, which try to span each node into some tree structure, which correspond to the neighborhood and the multiple hops of the neighbor. And then you can probably do the layer-wise comparison to check the distance between two graphs of different number nodes. So I think the graph isomorphism networks has already been used, right, for this purpose, right? You can probably check the recent paper from that group.
I will check that. Thank you for the suggestion.
Yeah, this is a very interesting question. Okay, so any other questions?
Yeah, Zhuo. So actually, I have some questions, and the first question is that so your entire talk is mainly about the spectral methods and like to apply, for example, apply it to the graph learning problems. So here's a very interesting because we know that like for the graph neural work, so we know that so the original study actually rooted from those of the graph signal processing, and they also use like the spectral method for that, right? But then gradually, so you know that the current mainstream research effort in the graph neural work that they prefer to use the spatial domain method, right? Directly operated or manipulate on the input graph instead of to solve the problem from the perception of the spectrum domain. So I was wondering, so how do you view kind of this type of current paradigm and whether your approaches that can help to provide some new insight for this?
Yeah, I think this is a really interesting question. We already we have seen before, right? But I think your perspective is kind of more novel here. I think the spatial method to me is probably more related to some other spectrum of the graph. So basically, if you look at the structure properties of the graph, it's corresponding to the first few smallest eigenvalues of the Laplacian. But the spatial domain, right, will be kind of more interested in some slightly higher eigenvalue than eigenvectors. So for example, in this Garnet problem, right, attackers may just introduce some new edges to some local regions of the graph, right? This will actually impact some really high eigenvalues of the graph structure. So probably spatial-based method can be used to do this, to detect those edges. But here, what I want to say is that although people may prefer spatial method over spatial because of the cost, I would say the cost is one issue, right? Another issue is how can we utilize slightly higher eigenvalue in the spatial domain, right? Traditional method, as you can see in the original graph neural networks that use the first few Laplacian eigenvectors, they only care about the first few smallest eigenvalues. But if we can further extend our scope to mid-range eigenvalues or even to higher end of the eigenvalues through some local filtering techniques, we probably can combine some concept in the spatial domain with the spatial domain. So in my opinion, spatial-based and spatial-based are not fundamentally different, right? It depends on what kind of spectrum you are looking at in the eigenvalue distribution space, right? if you look at more local information, it's related to spatial and probably related to higher eigenvalues. But if you are caring more about the global structure, then the lower end of the spectrum will be of our interest. If I understand spatial definition correctly, right? You mentioned some spatial.
Thank you. And there's another question. Okay, I think that is for me. So will the recording be available and how can access? Okay, so all the recorded talks you can find by this link. Yeah.
Okay. Yeah, I think this will be available, right?
Yeah.
Yeah, actually, in recent days, we try to quantify the Lipschitz constant of graph neural networks for embedding task. The goal is to find out the non-robust node samples, which can be easily perturbed, right? If you perturb this input node, then the graph embedding result will be totally wrong using some existing method. So yeah, this is some ongoing work. Also, we are kind of studying some more efficient neural network training method by leveraging the graph learning approach, right? You can always look into the correlation between the training samples so that you can probably reduce the batch size and epoch size so that you can probably accelerate on the edge device for training. Yeah, so that's some ongoing direction.
Sounds very promising, yeah. And if nobody else asks question, I will ask another. I will ask another question. And the second one is that so here we know that for when you want to use the spectral method here, so the by default choice that so we used the Laplacian transform. So I was wondering whether it is possible to consider other type of the transformation, because we know for the in the image, so you can typically we use the DCT, right, or the wavelet and so on. So because I don't work on those the graph signal processing or stuff, so I'm just curious about that. So is there any other alternative that we can consider to apply to other transformations, or even we can design some new transformation, or why the Laplacian is kind of the more suitable one in this scenario?
Okay, so the reason I would like to always use this Laplacian matrix concept to explain the spectral graph theory is because it has some very rigorous mathematical definition and derivations, right? You have a lot of proofs so that you can blindly use it without any trouble. Definitely, people can also use adjacency matrices, right, to encode the structure of the graph and apply all kinds of different graph filters based on adjacency matrices. The graph wavelet approach, right, are kind of also care about kind of concentrating on some local properties of the graph. So I think this is not the only approach you can use, right? Laplacian is definitely not the only one we can study, but I would say there are some existing theories that will support your proposed method, so that you don't need to prove, right, everything. But if you propose some new idea, you need to first prove it's correct for all cases, and then you can use it. So to me, I haven't seen any work that has established a very solid foundation, right, using matrices other than Laplacian. But I would say Laplacian is just a way for thinking about the graph structure and the properties. So once we understand the underlying principle, we can definitely simplify some operations. For example, we can design our graph compression algorithms based on alternative metrics, which can be slightly different from what I've been talking about, right? Those operations can be more efficient to accelerate and they can produce a similar quality result. So I would say, yes, normalized Laplacian, normalized adjacency matrices are of a strong interest in theoretical work, where a lot of support are available. But in practice, right, people are using some other ways to quantify or to probably design the algorithm. Right. For example, you can always construct some hierarchical trees from some given node where the tree structure encodes the neighborhood of 1 hop or 2 hops. And in this case, you can also capture the information of the graph structure, right? Then people can use it to check the distance between 2 graphs, as I mentioned in response to the previous student question. So yeah, I think, yes, spectral method should not be the only way, right? I think the better way is to probably combine spectral and spatial method to probably develop some new algorithms. But yeah, although I'm not kind of working on some related work at this moment, but I look forward to discussions if there is any plan.
And my last question is that, so that's a kind of more technical question. So I think for your robustness work, so if my understanding was correct, so as you mentioned, you don't need the model weights of the weights of your model, right? And you can only to examine the data, the structure
Yes.
of the data, and then to determine the robustness of the model. So then I have one question. So because we know that, so for those of the adversarial example, so I think it depends whether it is actually adversarial or the kind of benign or the adversary. It depends on your model, right?
Yes.
So because when we want to to craft the adversarial examples, so typically we will know that maybe no, for the white box attack, so we use the model to design that. For the black box attack, yes, we can use the transferability of the attack. But from my understanding, so the concept or the adversary or not, so actually it is not kind of the absolute. So for one example, that is kind of adversary to, it is to one model, maybe it's not to another model.
Yes,
right?
That's why this is data and model dependent.
Yeah, so but for your method, so you only need to examine the data itself, and then you can evaluate the robustness of the model. So in that case, so actually you decouple the dependency between the data, adversariality of the data and the model. That is my question. So
here I think I had to probably clarify a few things, right? Here we examine both input data as well as output data, which is kind of last layer features.
Okay, I see. So that makes
the model
sense.
information has been implicitly reflected in this output, right?
Okay, I see. Okay, so that makes sense.
So, yeah, so as you can see, for the input space, we quantify the distance, right, between samples, and our output space, we can also quantify the distance in a similar way. Then we only need to check the ratio of the 2 distance. If 2 samples at input are very close to each other, and the model try to map them to full distance samples, it means this model is not reliable, right? If you make small perturbation along this direction, right, along this P to Q, then potentially it will just create some drastically different prediction.
Okay, that makes sense.
So that's why we call this black box method, which doesn't require any labels to be given, right? Not any information about the model itself. So we can only look at the input and output data. Here, there is an assumption which may limit its application, which is we assume this input and output data samples all lie in the low dimensional space, which sometimes may not be true, right? So if you apply this to ImageNet data set, where the data sets are in high dimensional space, we have to do some transformation first, right? You need to convert it to relatively low dimensional space, and then you apply this method. That will work. However, if you directly construct manifold corresponding to the original image samples, that may fail. So have you ever considered to further to improve a method to make it kind of scalable to the high dimensional? So you need to probably design some encoder, right, structure, which can map the input data to some slightly lower dimensional space. So here I would say for MNIST data set and Cypher data set, we don't do any transformation. We directly use the input data samples, which have a few hundred or thousand pixels. This method still works. But if you apply it to ImageNet, then the dimensionality will not allow us to accurately estimate the Lipschitz constant. Then you probably can do some, for example, transformation, right? You use some existing network structure to convert it to low dimensional space, then you do the check.
Okay, thank you. Yeah. So this is a very elegant method. I like your idea. I think there's
thank you.
Another question in the chat box.
I think there is another question. Can such robust statistics area part of training? Yeah, that's very interesting question. So I'm not sure if this metric can be efficiently computed on the fly because it requires some calculation of eigenvalues. We do have some fast solvers for finding the eigenvalues and eigenvectors, but the time is still large, right? If we can quickly estimate this, there is a chance. In recent months, we are working on applying this idea to graph neural networks, and we already observed very interesting results. So if you have any kind of applications, right, which does not care about the training time, we can test it. Otherwise, as you can see, we need to always compute, right, this kind of generalized eigenvalues. Fortunately, our paper also proposed some fast solvers for solving these eigenvalues quickly. For even data set with a few tens of thousands of samples, we can still get a solution within just a few seconds. If this is not a limitation, we probably can consider that, right? Yeah, I think hopefully I explained the limitation, right, of this work. It actually assumed the input data to lie in a relatively low dimensional manifold space so that the graph construction phase can truthfully reflect the original topology of the data samples.
Other questions from the audience? So actually, the last questions from the audience, actually, it inspired me another questions. Yeah, so I was curious about those, whether this approach, so you are to measure the adversarial robustness, can be applied for some like the current application, like to detect like the fake image, like the fake video, or like to detect the weather. So the generative, the results from those, the generative model, like the diffusion and so on. So
yeah, I would say as long as the model try to learn some distribution, right? Then this distribution usually corresponds to some low dimensional manifold structure. However, if you have some adversarials, this may be off the manifold, and sometimes those can be difficult to detect. But again, I would say this is depending on the models and data sets, right? Here, we only introduce a very different mathematical approach for quantifying these things in black box manner. But black box method has its benefit and disadvantages, right? It uses minimum information, but if we can leverage some model structures, right, and combine the black box method with some model information, probably we can do something, as you mentioned, right, more effectively. But I don't know. I haven't tried that. But my understanding is that those adversarials may not lie on this kind of, may or may not lie on the low dimensional manifold, depending on how you define the dimensionality. But that'd be a implication. I have never heard about it, but I think this is related, right?
for example, whether if you want to launch or to examine the vulnerability of those the GPT that against the adversarial attack. So because we know that for ChatGPT, so their model is not kind of open source or open release, right?
Yeah, that's interesting. I think if we can find the low dimensional embeddings of the input, and we can find output samples, then we can do this, right? Otherwise, if the input is some really high dimensional data sample, we need to do some transformation, maybe using transformers first, and then we can probably use this method to detect. right? Although it's not open source, but it's based on transformer, right? We probably can apply transformer to apply to the input, and then we get some low dimensional embedding, which will be fit into probably the following stages, which we don't know, right? If it is transparent at this moment. But here I think applying this method really require the input and output lie in a relatively low dimensional manifold space. So that's a limitation. So that's why we cannot get a good result for ImageNet data set directly. But I believe we can here reasonably handle dimensions like Cypher or the MNIST data sets. Yeah, I think what you mentioned is very interesting direction, right? Which deserve investigation, but we probably need additional step to transform the input to some low dimensional first.
Thank you. Thank you very much. So if there's no more other questions, so let's thank our speaker again. So Zhuo, so this is very interesting work. So thank you so much.
Thank you, Prof. Thank you.
Great
Let me know
talk.
if you have any question. Yeah.
Fantastic talk. Thank you so much.
Oh, thank you, James.
So also thank everyone to attend our this week's seminar talk. Okay, thank you. Have a wonderful day.
Thank you. Bye bye. Have a good day.
Bye.